So if you want to be a math major, or if you are a math major already, then you need to know how to prove something like this. I saw this question on the National Taiwan University entrance exam for transfer students. This is their Calculus A test, mainly for math majors. Let's have a look. We have f being a differentiable function on R such that f of 0 is equal to 0, and the absolute value of its derivative is less than or equal to the function, true for all x. We will show f of x is equal to 0 for all x from 0 to 1/2. The truth is, with these conditions, f of x is equal to 0 for all x. But part A actually just wants to prove this part, which is a great hint. Even though we have this hint, at first, I couldn't get it. I had to check with my new friend, which is Google Gemini for the solution. I think this solution is the simplest one, and I want to demonstrate the solution along with my thought process along the way. So here we go. Firstly though, how do we show an equality? You can think about an equality for two numbers, because if you put a number from here to here, the result is a number. The answer is that we will show greater than or equal to and less than or equal to. Because once we have these two inequalities, they have to be equal. And now, what do we have? Differentiability for f. It seems that it's not a lot, but the truth is, it is a lot. We have the mean value theorem that we can use. That's pretty much the main tool for this right here. And once we have differentiability, we also have continuity for f. Maybe the intermediate value theorem, and there's actually something else that I'm going to tell you later on. So, have a look. I want to start with the mean value theorem, and to do so, we will have to write down the usual details. So, let's just go ahead and write that down. F is deable on R implies that we have f being continuous on the interval and deable, of course, on the open interval. That's the usual thing. Then we can quote the mean value theorem. There exists some number c on this interval such that, and this is the statement, the derivative at c equals the slope of the line between the endpoints. Okay, f of 0 is 0, but now what? This is just a number, and then I don't think we have a lot to work with, right? Because what we're trying to show is f of x is equal to 0, true for all x from 0 to 1/2, but this is just 1/2. What can we do? The problem with this is that if we only put down 1/2, then we are being restricted and it's not going to help us get anywhere. So instead of the 1/2, we are going to change it to a variable. Let's just keep it as x, and we will have more things to work with. And right here, let's go ahead and denote x is in between of 0 and 1/2. X could be equal to 1/2. If x is equal to 1/2, then that's the same interval as that. All right, and then such that this time we can write f prime of c equals f of x minus f of 0 over x minus 0. And that is equal to 0. Now, we have f of x. Just like what we have right here. Much better, right? So perhaps let's isolate f of x. Multiply the x to both sides. So far, so good. But now what though? Have a look. We want to show these two inequalities, and we do have this inequality that's given. We have the derivative. But before we can use this inequality, we need the absolute values. And in fact, if I take the absolute value to both sides, I get an inequality right here for free. Because absolute value of anything, it's always going to be non-negative. And right here, absolute value of x times absolute value of f prime c, because the product of the absolute values is equal to the absolute value of the product. But absolute value of x, the absolute value doesn't matter, since x is just positive. And then we can see that we have this inequality to use. So replace the 1/2, and then we see that this right here, absolute value of f prime of c. We can use this inequality to help us out. True for all x, of course, it's true for the time when we have c. And this is less than or equal to perfect. So we just have to replace f of c in the absolute value without the prime for that. So far, so good. Now let's think about what we have. I know we have absolute value now, but if we can show this, it's in between of 0 and 0, then that means absolute value of f is equal to 0, and we can also say that f has to be 0. So I hope that this is equal to 0, but how though? Yeah, this is perhaps the hardest part because we have to think about what other tools that we can possibly use. Okay, differentiability gives us continuity. When we have continuity, yes, we have the intermediate value theorem. On the closed interval, let's say AB, this is just a idea. Okay, so let's say we have f of A, f of B. The function is continuous, so no matter how you connect it, you get something like this. The intermediate value theorem says the function takes the values between here and here. I cannot guarantee anything above. But that doesn't really help because we're trying to work with inequalities. Instead, we can use the extreme value theorem because we have a function that's continuous on a closed and bounded interval. That means we are going to get an absolute max and also an absolute min. So we can say the function, if you take the absolute value of it, it's going to be bounded by some number. Usually we call it m. So the extreme value theorem is the key. And we have to make sure that the function is continuous on the closed and bounded interval because if this is an open interval, then the function can go shooting up. You have a vertical asymptote, you never get absolute max. But with this, we can use the EVT. And of course, just like when you use the MVT, you have to write down a little statements like this. So we will do that too. So I will say f is continuous on 0 to 1/2. Right here, the keywords are, you have to mention this is a closed, meaning you include the endpoints, and bounded, meaning it's a finite length for the interval. So with that, we can say by the extreme value theorem, as we said earlier, the function is bounded above and also bounded above and also bounded below. I can just write this down right here. There is some capital M in the real such that the function, once you put in the absolute value, is less than or equal to m. And this is true for all x on the interval that we want. Now, have a look. This is true for all x. Of course, it will also be true when x is equal to c, because c is somewhere on this interval. So I can say, so absolute value f of c is less than or equal to m. And yes, we can put this right here and we get half m. Almost there. Almost there. In fact, this right here is just the first part of the extreme value theorem. We have the function being bounded, but the second part says the function must get to the absolute max and also must get to the absolute min. So in math, we are going to write this down. I'll just say also. I will just say there exists some number on this interval. I will call it x0 on the interval 0, 1/2. That f of x naught is going to be the max, or if you would like to say f of something else, it's equal to the minimum. But right here, I'm just going to say that such that because I want to work with this inequality, with this notation, you will see I want to take the absolute value such that f the absolute value of f of x naught. Also because I don't know that the min, max, or whatever, but I just know that this thing, once you plug in that specific x naught, you can get to m. we just know that the function has to get to m somewhere, okay? Because the m could be the absolute value of the lower bound, right? Because like maybe this is like the smallest value is -3, and then the maximum value is +1, but you'll say m is 3 because you have the absolute value. So there is some x naught on this interval such that this will happen, guaranteed. Now, have a look. We have our first thing right here. This is the first thing that we have, and this is the second thing that we have, and we have the third thing that we have here. Well, if you combine number 1 and number 2, so note that 1 and 2 gives us what? I'm just going to replace the m right here, so we get absolute value of f of x is in between of 0 and 1/2 m. Combining the first inequality here and the second one. And with third, I can replace the following. Because this right here is true for all x on this interval. Well, it must be true once you get to x naught. So with number 3, we can say absolute value of f of x naught is less than or equal to 1/2 m as well. And then finally, we know this right here is equal to m. Alright, m is less than or equal to 1/2 m. What is m? The only way that this can happen is m is equal to 0. So as you can see, this right here is indeed in between of 0 and 0. So if you would like, you can call this number 4. So finally, with number 1 and number 4, we can get absolute value of f of x is indeed in between of 0 and 0, which implies absolute value of x is equal to 0, and that means f of x has to be equal to 0. What's x? X is anything in between of 0 and 1/2. Don't worry, I know we are not including 0 in this case here, but remember f of 0 is equal to 0. So I will say n because f of 0 is equal to 0. In fact, we are done. Because f of x is equal to 0 for all x from 0 to 1/2, just like this right here. Okay? Now, for the second part, you guys can think about how to extend this proof so that f of x is going to be equal to 0 for all x. Right, I'm going to leave that to you guys. And I do want to give you guys another question to think about though. The reason that you get a 0 function is because you have this condition, f of 0 is equal to 0. If today I tell you f of 0 is equal to, let's say, 1/2, can you find a function that will satisfy this condition? And I'll tell you the answer is, of course, not going to be the 0, 1, 0 function anymore. In fact, also, well, it could be the 1/2 function, but that's too boring. Don't give me the 1/2 function. I'm going to leave the answer in the comment down below and let you guys know. You guys can see the pin comment. That's it.